cast implementation and reason in terms of the reference implementation. So I'll run red-black trees, but anytime I want to do a proof about it, I'll transport to cast it to lists and reason about the list code. Okay, so this is pretty cool. Let's see. There's one more thing that I want to talk about, which is the idea of computationally relevant quotients. And I know I've got like a minute, and that's fine. Computationally relevant quotients. So not only can we equate things, but just like with univalence, we can equate things in such a way that the way in which they are equated, like bijections, has computational content. Okay? And there are some nice examples of this, like if you look in the logical relations support code for lab 3-logical relations, there's this data type of terms in context gamma. And there's a whole mess of lemmas about variable binding constructing these terms in context gamma. Okay? We can clean up all of that mess in homotopy type theory by considering a type of context where what it means for gamma to be equal to gamma prime is in fact that there is some substitution theta between gamma and gamma prime. Okay? So this almost works. The problem is that we need to generalize to something called directed homotopy type theory because substitutions are not symmetric. So this is an even more work in progress idea than homotopy type theory. But it's pretty clear that you can generalize all of these ideas to something that drops the symmetry requirement. And therefore, you can have gamma less than gamma prime mean something like there's a substitution in context gamma for gamma prime. And then just like transport wrote the code it wrote today, it's going to write all of the proofs about variable binding that are in that file or that were in Stephanie's Unbound library from this morning for you. Okay? You can get those to fall out of functoriality if you choose a directed notion of equality. Okay? Another thing you can get to fall out, just since this one came up in Amal's lecture, if you want, what was it? E sub k of E to have a map to E sub j of E whenever k is less than j. This was exactly an example of functoriality. The type of predicates is a functor from a type of natural numbers where the paths here are less than. Okay? So there's lots of these kinds of things that come up. And I just wanted to just like throw a bunch of stuff on the board to suggest that there's some stuff to do. Most of these are like ideas that no one's really fleshed out. So if you're interested in working on this stuff, then definitely talk to me. OK, so like end of today's lecture. And just to sum up where we went. OK, so the other thing that I didn't even get to write on the board, but there's lots of applications to using homotopy type theory to formalize math. So I was kind of focusing on programming languages things here, but there's a lot of applications on the math side too. OK, so this is the end of the Agda lectures. And by now, you've had a little bit of time programming in Agda and programming in Coq. And we didn't really get to talk about the contrast between the two. You'll have a little bit more Coq when Steve talks about LLVM starting after lunch. 2:30, yeah, OK. So you'll get that then. But like in terms of the contrast between Coq and Agda, I just want to say one thing, which is, has somebody used the line that Coq is like playing a video game yet? Yeah. Okay. Yeah. OK. So the question you really have to ask is, what kind of video game are you playing? OK. Coq feels to me, and this is of course a subjective consideration, kind of like, did anyone play like Dragon Warrior or Final Fantasy on NES? OK. So like, there's a lot of menus, and you spend a lot of time like pressing the A button repeatedly to level up. And if you press the A button enough, then you eventually get through your proof. But it's not particularly pleasant, and you kind of want to like sit your little brother down and be like, here, Matt, press A for, OK, thanks. Okay. And in Coq, you can actually just like write a program to do it. Like you write a tactic to press the A button repeatedly, and eventually it solves your goal. Okay. On the other hand, to me, Agda feels more like Tetris. Okay. There's about like 5 pieces, right? What are the pieces? There's inductive families. There's dependent pattern matching. And it's all about how you arrange these pieces. We saw in these lectures that out of inductive families and dependent pattern matching, you can do things like intrinsic and extrinsic verification. We did some universes for generic programming, the data description language, functoriality. It was really the same tools, just kind of arranged in different ways. Okay? And there are trade-offs between the two. In Agda, like you end up with the pieces stacked in an unwieldy way, and your code just scrolls so far off the right of your screen that you just give up on doing your proof. Okay? You lose. But sometimes the pieces fit together really nicely, and you get a really nice, clean, elegant, readable piece of certified code. And I think that's really what people should strive for with dependently typed programming. OK, so thank you for paying attention. There'll be a hands-on session this afternoon, and see you later. Thanks. OK, questions? Yes. Yeah. So what I would say to that is that like the implicit arguments and support for unification and stuff like that in Agda really makes it easier to write proof terms in Agda than in Coq. But on the other hand, these two are getting closer together, and there's no reason you can't have a tool that both has tactics and has nice proof terms. We just don't have that right now. OK. Any other questions? All right, lunchtime.